All right. So, again, we're going over the notes. Does somebody have a question? Okay, we have to get another one. Why don't you come up here and get one of these star charts? Okay, so I'm going to do a notebook check on Monday, just so you know, all right? I'll be looking for this thing that you taped in there today that shows the periodic trends. And again, tomorrow we need to have pages 4, 5, and 6 done. So the first thing I want you to do is turn to your periodic tables that are in your notebook. And I want to talk, this is also the first part of your notes, I want to talk to you about periodic law. Essentially what periodic law is, it's just the trend of when you organize elements by atomic number, you see a repeating pattern of characteristics. Okay, that's the periodic law. We see things start to repeat when we put things in order from atomic number. So the very first periodic table was developed by this fellow named Dmitry Mendeleev. He was a Russian chemist, and he developed his periodic table in the late 1800s. And it was pretty cool. He knew at that point there had been lots of elements that were discovered, and so he knew of those elements, and he started organizing them in order of increasing atomic mass. And he also noticed some of the repeating patterns in those elements, and so he kind of started lining them up. And he noticed that there were some gaps in the masses, and he thought, well, maybe these gaps are showing places where elements that we haven't discovered yet might be. And so he was absolutely right. And he was able to predict some of the characteristics of those elements that hadn't even been discovered yet by putting them all on that periodic table. So that was really cool. But there was a problem with the way that he had those elements listed by mass. Okay, sometimes masses change a little bit depending on the element with isotopes. Hey, you too. Knock it off. So close. You too also. So this other guy, okay, this other fellow, his name was Henry Moseley. He was an Englishman. He said, I know how we can fix this little problem with Mendeleev's table. Instead of organizing the elements by atomic mass, we'll organize them by atomic number. And so that way, since that number doesn't change, since that's the number of protons, we'll just line them all up and it'll be just beautiful. And so that's kind of the way it went. And it was just beautiful, beautiful, beautiful way it was. Okay, so your periodic table. Your periodic table should look something like the one that I have here. Okay? In the center, we have our transition elements. And you might notice on the transition element, I don't know what you're doing. On your transition element, the groups are a little bit different than they are on these other parts that are called representative elements. The transition elements, their group numbers are followed by a letter B. Okay, so that letter B indicates that the elements that are in columns that are indicated by the letter B are transition elements. And they're numbered kind of funky. They start out with number 3 and they go 4, 5, 6, 7. There are actually 3 groups that are part of the 8B, and then it starts over again with copper at 1B and 2B. Okay? So what you need to know is that if they're in a group that has the letter B, that they're called a transition element. Okay? If they're in a group with the letter A, they're called a representative element. Representative elements are representative of the trends that we see on the periodic table. Right? So on page 5, I think it was, or maybe it was 4, there were questions on there that asked, are these elements representative or transition? And that's what it's asking you to distinguish. So if they fall into this category, or if they're down here in the actinides and lanthanide, then they're a transition. If they're not here, then they must be a representative. Okay, so that's what that part was asking. The next part that I want to talk about is the octet rule. Okay, and in order to talk about the octet rule, we need to start talking about ions. So first of all elements are trying to get to be stable. Right? They want a stable electron configuration. So, the only elements on the periodic table that are completely stable are the noble gases. And they have, with the exception of helium, a completely full s orbital and a p orbital, which gives them a total of 8 valence electrons. So 8 is the magic number that we're trying to get to. Okay? You guys should be following along and taking notes in your notebook. Okay, I'm reading at 3.3. So this is the part where you might want to start writing some stuff down and reading at 3.3. Okay? So they're trying to get to number 8, right? So if we look at sodium, okay, the metal sodium, how many protons does sodium have?
Sodium?
11. Good. So if it's a neutral atom, how many electrons would it have? 11. Okay. So sodium's Bohr diagram, we would start on very first energy level, and we would put 2 electrons there. That's all it can hold. On the second energy level, we could put up to 8. That gives us a total of 10 so far. So the 11th electron will go on the outermost energy level. And that electron on the outermost energy level is sodium's valence electron. Okay? So sodium wants to have 8 valence electrons, trying to get to that magic number of 8. So far it has 1. So how many is it lacking to fill this outer energy level? 7. So in order for sodium to become stable by gaining electrons, it would have to gain 7. And that's a lot. That's a lot to gain. And it takes a tremendous amount of energy to do that. And sodium doesn't want to spend that much energy getting electrons. So instead, what it does, instead of gaining electrons to fill this energy level, it kicks this one off. Okay, so this electron leaves and becomes a free electron. And once that happens, this outermost energy level kind of goes away. Okay, because there aren't any electrons there anymore. So this sodium atom changes into the sodium ion that has 2 electrons in its first energy level and 8 electrons in its second energy level. It's still sodium because it has 11 protons in the center, and that's what gives our elements their identity. But it's lost an electron, so this is now called the sodium ion. And it has a 1 positive charge. The reason why it has a 1 positive charge is because it started out with 11 protons. And it also started out with 11 electrons. But when we remove that 1 electron, now instead of all of these canceling out, one of them doesn't cancel. And we're left with an overall positive charge. So we indicate that overall positive charge by writing a superscript of 1 plus. Okay? This is called an ion, right? An ion is an atom with a charge. Okay, an ion is an atom with a charge. So it's not neutral. The charge can be positive or it can be negative, and you get a charge by either gaining electrons or losing electrons. Okay? So in this instance, sodium loses an electron. Okay? It lost an electron, which gives it a positive charge. Elements that become positively charged when they form an ion are called cations. I used to think it was cations also because my science teacher told me That's what it was. So when I went to college and I was calling these things cations and anions, I looked like a complete idiot. Which probably wasn't too far off base. Okay, so sodium, this is called the sodium cation. The sodium cation. Right? So let's look at the opposite. Let's look at chlorine. Right? How many electrons is chlorine going to have? Wrong. 17. Okay? So chlorine has 17. So on its first energy level, there are 2. Second energy level, there will be 10. And third energy level, in order to get to 17, there will be 7 electrons distributed around. Okay? So what's again the magic number that chlorine's trying to get to?
8.
8. Trying to get to 8. It has 7. So what is it going to do? Yeah, instead of how sodium got rid of its electron, chlorine just really is lacking 1. Okay, so it's going to pick up an electron from somewhere, right? And it's going to use it to fill that empty space there. All right. So chlorine has gained an electron. When you gain an electron, we call that ion an anion. Anions are negatively charged. So now, since this gained 1 electron, the chlorine anion is Cl with a 1 minus charge. It's fine, huh?
Oh, no.
Riveting. It's riveting. Okay? So that's ion formation. Okay, so on your guys' periodic table, it's in the middle of your notebook. Flip to that really quick, because we're going to add some information here.
Hey, which periodic table?
So the big one in the middle, the main periodic table in the middle. All right, so if you have colors, that would be lovely. If not, it's okay too. Just make sure you're labeling these. The blue ink is going to represent our valence electrons. Okay, this is review. How many valence electrons? How many valence electrons are in group 1 element?
1.
Good. What about group 2?
2.
What about group 13?
3.
Group
4.
14?
4. 5. 6. 7.
7, 8, 9.
Good.
9.
That's up to 8. Okay, great. So the other number that you're going to write up there is called an oxidation number. Ooh, big word, yeah. Sometimes it's also called the charge number. Okay, and all that tells you is the amount of electrons that are either going to be gained or lost for elements in each of these groups to become stable. Okay, so it's sodium and hydrogen, well, let's leave out hydrogen, but it's sodium and lithium and potassium and francium, all these elements in group 1. Okay, if they're going to get to their stable configuration, what's going to happen with their 1 valence electron? It's going to get kicked off. Okay, they're going to lose that electron. So if they lose 1 electron, what's their overall charge number?
+1.
Positive, okay? That was a hard thing for me to remember too when I was in school. When you're losing something, you automatically think negative. But what you're losing is negatively charged. So you end up having more protons, which are positively charged, than you have electrons, which are negatively charged. So when you lose an electron, you have an overall positive charge. Okay? So what about here in group 2? How many electrons are these things going to be getting rid of? 2, okay, because they have 2 valence electrons. So what would their overall charge be? 2 positive. Good. And you guys can write these 2 positive, you can write them positive 2, okay? It doesn't matter which way that you write them. You can go either way. For some reason, my brain is always set this way, so that's the way it is. Okay, over here to group 13 elements where boron is, they have 3 valence electrons. How are they going to get to that stable 8 number? They have 3, they're trying to get to 8. Is it going to take more energy, do you think, to get rid of 3 or to gain 5?
Get rid of 3.
Yeah, well, we want to get rid of 3. Okay, these are going to they're going to kick 3 electrons off. Okay, so what will their overall charge be if they get rid of 3 electrons? 3 plus. Okay, on this one we're going to put a big X over the 4. Okay, these group 14 elements like carbon, they can either gain 4 or they can lose 4, but most of the time they just end up sharing, right? So we don't really put them into this trend. So we're just going to put an X there. Okay, so now over here these nonmetals. Okay, over here the nonmetals. If they have 5 valence electrons and they're trying to get to 8, does it make more sense for them to kick 5 off of their outermost level or to gain 3?
Gain 3.
So what will their be overall charge if they're gaining 3 negative? 3 minus. Okay, 3 minus is the oxidation number for the group 15 elements. So what about if they have 6 valence electrons? Beautiful. They're going to want to gain 2 electrons. 1 minus. And what do the noble gases do?
There's not.
Nothing. Beautiful. Very good. Okay, so now on this assignment where it talks about filling out oxidation numbers, now you have the oxidation numbers for all the representative elements. Okay, so if I asked you what is fluorine's oxidation number, you would tell me
1 minus.
1 minus. If I asked you what is magnesium's oxidation number,
2 plus.
2 plus. Okay, easy peasy. Easy peasy.